2018 breadth paper, question 26. The last part of, well, actually the middle to last part of question 26 was quite poorly answered by most students. The first part, part A of question 26, is a straightforward calculate the wavelength. You'll use the wave equation. Because it's a microwave, the velocity will be the speed of light. Make clear that substitution. Rearrange the equation to make wavelength the subject, and that's going to be the speed of light divided by the frequency. Always show this part of your working, put the numbers that you're going to use, so the speed of light 3 times 10 to the 8 divided by 11 gigahertz, and I guess you just need to know that giga is times 10 to the 9. Plug that in onto your calculator and it should spit out the answer 0.0272727 recurring meters as the wavelength. And as I consider writing my final answer on the dotted line, I'll always take a cursory glance to see how many sig figs have been used in the numbers given to me in the question, in this case 2, so I'll write my answer to 2 significant figures, 0.027 meters and no more. This next question, the receiver detects no microwaves in the positions shown in figure 26.1, and the reason for that is because the gap is quite big and therefore you're not getting any diffraction, and so the receiver is not in the line of sight of the microwave transmitter. In this picture, the gap has now been reduced. It's not the gap being smaller is not the reason why you get diffraction. By the way, diffraction looks something like this. The reason why you get diffraction is because the gap is comparable to the wavelength. It's not because it's smaller. You can't keep making this smaller and smaller and smaller and get better and better diffraction. You'll only get good diffraction when the gap is comparable to the wavelength of the microwaves. So consequently, the sort of thing you need to be writing here is, because the slit width is now comparable to the wavelength of the microwaves, the waves diffract as they pass through the slit. If you use the word diffraction in your answer, that would be worth 1 mark, and if you mentioned that the gap was comparable, you got the other mark. But if you talked about the slit just being smaller, and that's the reason why you got diffraction, I can't be giving you the 2nd mark there. This question, very few people were scoring all 3 marks here. Most people were scoring 1. And it talks about light travelling from air to water in a refraction type situation, and it asks you to compare the speed, frequency and wavelength of light in air and in water. So initially, making this little slideshow, I started to sketch myself a picture showing a ray going from air into water. It'll slow down or refract towards the normal, and then I wanted to try and illustrate this by adding some of the wavefronts, and it just started to turn to crap. So I thought, why am I bother drawing this? Why don't I just have a quick search on the old Google and find one that's been made already. So what you should be able to notice here is we're refracting towards the normal, as you would expect. The speed is reduced as we enter the water, but notice how the wavelength is long in air and shorter in water. And then the final thing that we have to consider is frequency, and probably the best way to move forward here is to actually get a video off of YouTube. And as you watch the wave fronts go from air into water, you can see them slowing down, moving more slowly, having their wavelengths reduced. And if you were to sort of observe the frequency with which the waves are passing the cursor, both in the air and in the water, it should be identical. So let me just turn that back so we can watch it some more. And it should be that here they're moving faster but have longer wavelengths, and here they're moving more slowly but have shorter wavelengths, and the 2 things should produce exactly the same frequency. So the 3 marks are available for saying the wave speed is slower in water. Some people were just writing the wave speed is slower and then full stop, and then because it's not clear whether you're saying the wave speed is slower in air or in water, I can't award marks there. So be specific. The wave speed is slower in water, the wavelength is shorter in water, and the frequency is unchanged between air and water. Part C, classic experiment. I think it's one of the PAGs. The question asks for how would you determine the critical angle, and how would you hence find the refractive index of the glass. And initially my sketches here are going to be the sort of wrong diagram that people were drawing, so I'll make that red. This is all wrong. So if I start with indicating the normal as our reference line, and then adding a ray box on the top side above the flat side of the glass block, ray striking this surface with an arrow to show that it is a ray going in that direction. I can even finish this off by saying as it enters the glass, it'll slow down, refract towards the normal. I can label the angles, I can label the angle of incidence, I can label the angle of refraction, and this is a physics diagram is fine, everything's good. The trouble is that if I move this ray box around now, I will never ever get to the critical angle. I will never be able to demonstrate total internal reflection under these circumstances. It's impossible to get this ray to reflect off of this surface in this circumstance. So what you really have to do is have the ray box shining from below, striking the midpoint, crossing this boundary at 90 degrees so its direction is unchanged. Always put an arrow on a ray. A line without an arrow is not going to score you points. As it goes from glass to air, we're going to speed up and refract away from the normal. And you can see how this refracting away from the normal leads to the critical angle. We want to keep moving the ray box to the left in this, in this diagram, until we end up with the situation exactly like this, where the refracted ray grazes the surface of the glass block. The angle of refraction would be a right angle, and the angle of incidence that causes an angle of refraction of 90 degrees, that angle of incidence is now known as the critical angle. You can measure this critical angle from the normal to the ray using a protractor, and then once you have that angle, you can then calculate the refractive index of the glass using Snell's law. So Snell's law is n1 sine theta 1 equals n2 sine theta 2. Let's make subscript 1, let's change that to air, and subscript 2, let's change that to glass. The refractive index of air is near as damn it 1, so let's just remove that bit. The angle in air is 90 degrees, and sine of 90 is 1, so that goes as well. The refractive index of glass is what we're looking for, and the angle in glass at the moment is the critical angle, so I can make that substitution and then rearrange this equation to get refractive index of glass. You would literally just do 1 over the sine of the critical angle. So the sorts of things that you might get marks for is a description of the experiment and a decent diagram, the really simple statement of measure the critical angle with a protractor. I know that sounds silly, but that's something we're definitely going to practice as we lead into the exams. And a third mark possibly for how you would calculate the refractive index of the glass using a broken down version of Snell's law, where the refractive index of the glass is 1 over sine the critical angle.